And we're going to start off with a story out of the University of Toronto, which is this new study about how AI-generated genomes promise to advance sort of precision cancer detection.
Yes.
And so that's sort of the story.
Mm-hmm.
And we cannot avoid AI.
We cannot avoid AI.
It's just it's becoming much more prevalent, and it's interesting because a lot of times people think of generative AI as, oh, let me create an image about
or ChatGPT,
or
right?
ChatGPT.
The G in GPT is generative.
And so a lot of people think of the consumer use cases, but in sort of this early stage research arenas, there are some interesting things happening. This being one of them.
Yeah.
So how exactly are the researchers at the University of Toronto using generative AI for this detection process?
Right. Well, the problem is precision oncology, okay? Mm-hmm. It needs a lot of large genomic data sets.
Yep.
But we also want to preserve the privacy of the individuals that are donating that data set, right? And so this creates a kind of bottleneck between the research and tool development for if we want to look at a genome, let's say, of a patient and try to figure out what is the specific cancer that this person has and how can we better mitigate that? What are the kinds of drugs that we need to actually do this? In order to actually train a model to do that job, we need a lot of data.
Mm-hmm.
But the data has to be, without all of these privacy bottlenecks.
The sort of personal identifiable information.
Exactly, yeah. And that's what's tough, okay? And this OncoGAN, which is a generative AI pipeline, it was published in, I believe, Cell Genomics. Cell Genomics, yes. OncoGAN.
Yes.
It creates a highly realistic synthetic cancer genome just completely within the computer, okay? And it bypasses these privacy issues.
That's actually really interesting, okay.
Right? And the key feature is it mimics all of these computational, complex, mutational landscapes that are characteristic of cancers, but it doesn't tie that data with the patient.
With an individual.
Okay? Yeah, and the goal is basically to democratize access to this high-fidelity genomic data, accelerate cancer diagnosis, treatment, prevention tools, all of the stuff that we want without actually compromising patient confidentiality.
The idea being if you can provide this sort of substrate of the data set, a variety of research teams and institutions can do of work towards solving the problem without running,
into all of the regulation right?
issues.
Which are there for a good reason.
Reason.
So let's go through what precision oncology means.
Okay.
Why it's actually hard to actually simulate these genomes.
Yeah.
And then what this current paper is doing. Okay. What this current paper is announcing. So the vision of precision oncology is we want to shift from things like chemotherapy and radiation, which is kind of just a general sort of shotgun approach, to this tailored treatment based on a patient's tumor, the molecular and genomic alterations in that tumor. Okay? And we want to make it precision. That's where precision comes from, right? And so what we want to do is identify mutations and then administer targeted drugs. Mm-hmm. There's a data bottleneck where we have this paradox between sharing and privacy, right? Because the success of precision oncology and an AI to precisely identify what type of oncology is going on depends on a vast, diverse data set, right?
Yeah.
But every single genomic identifier is something that is unique to every individual, right? You've got 3 billion base pairs, and if I know your 3 billion base pairs, I can figure out who you are, right? So re-identification is really possible. Like even if you de-identify data,
right?
Like you took some patient's genomic data and you took out some parts, it would actually be pretty easy to look up who you are based on genealogical websites, public records, the whole like 23andMe thing, Ancestry.com, like that whole thing, right? So there's privacy risks, and that can reveal dispositions to disease, potential discrimination, and you've got stuff like HIPAA that actually controls and creates barriers for that kind of data sharing. It's a very good thing that we're doing that, right? Because then Without it, you can have potential discrimination on life insurance, long-term care.
Right. I was going to say the big issue is you don't want insurance providers to be able to basically say, oh, because we know that you have, this is the whole Obamacare pre-existing conditions issue.
Yeah.
If we know who you are and what your pre-existing conditions are, we're going to charge you more because you're a higher risk and liability for us as the insurance provider.
Exactly. Yeah. You don't want that. That's just blatant nonsense.
Yeah.
Right.
Yeah.
The other thing actually that it's tackling is if you have an AI generated tool, whenever we make AI, you want to have a ground truth data set that tells you what is right or wrong, right? So that you can compare one AI model from another. Well, with cancer data sets, it's really hard to do that kind of benchmarking because the real patient samples have sequencing errors. You don't actually know what the tumor complexity is. There's no actual ground truth. So if we were to generate data sets that have a ground truth, then we can easily benchmark all of these other AI models. So when someone says, hey, I've got an AI model that I think does better, we've actually got a data set where we can test that.
Yeah.
Right?
Yeah.
So that's a separate issue from the privacy thing. But this thing is actually tackling both of them at the same time.
Interesting.
And obviously there's a huge economic and human imperative, right? Like there's a global cancer burden, 20 million new cases every year, 9.7 million deaths every year. There's a huge economic toll. Drug development is long and expensive, takes hundreds of millions of dollars. And if we have this kind of data set, we can train models that do it way better, right? We can limit all of that and democratize this approach.
This is actually totally an organic anecdote, but literally I was in a work meeting earlier today, and unfortunately one of my coworkers, has a partner that was just diagnosed with stage 4. And it happens every day.
Yeah.
It is present personally for millions of people. 1-2 degrees of separation for so many people.
Everyone knows someone.
And literally today, so this is clearly obviously a highly important and prevalent issue.
Yes, exactly. And so let's talk about like cancer itself.
Okay.
And why it's even like hard to do this.
Okay.
It's hard to like make these genomic data sets that are synthetic the way that we want. Okay. Cancer is a disease of the genome. It's caused by DNA errors. At the end of the day, that's what's happening. Okay. There's 3 billion DNA letters, ATGC, in our genome. And we're going to use this analogy of the genome being a library of cookbooks. Every single chromosome is a single cookbook that, let's say, one cookbook is for Indian food, one cookbook is for desserts, and so on and so forth, right? So the genome is a library of these cookbooks. Each cookbook is a chromosome, and then each recipe is a gene inside that cookbook. Okay? If we have errors in critical recipes, that's going to lead to cancer. And there's really 2 types of big mutations that happen, these typos that happen in our recipe. Okay? There's germline mutations, which is basically when a mutation is, right, when a letter gets substituted for another letter, or some mistake happens in the genomic reading of the thing, or I delete a bunch of letters, so on and so forth, right? There's 2 types of mutations that happen. There's the germline mutation, that's something that's inherited from your parents, and that's present in every single one of your cells, right? Because that's you came from a zygote, which is a single cell, and so whatever mutation was in that zygote
permeates.
That's all of you, right? Then there's somatic mutations. These are acquired during your lifetime. It happens within a single cell, and then the progeny of that single cell inherits that somatic mutation, right? Cancer is actually primarily driven by accumulated somatic mutations.
Not germline.
There are obviously cases where germline mutations create the cancer off the bat.
Yes.
But usually it happens with age, and there's these accumulated somatic mutations that cause your cells to do weird things, become tumorous, become carcinogenic, and then create the cancer, right? And one key aspect is OncoGAN, which is this generative AI. It's trained on and it generates only somatic mutations. It doesn't get trained on the germline info. So it's already getting rid of that sort of privacy
issue, which is important to understand that there's two entry points, one of which has less of a privacy concern by default. And that's where this OncoGAN is focused on.
Exactly. Yeah. Now, when it comes to the architects of cancers, there's two types of cancers. There's a driver and a passenger. So the driver mutation, these are critical alterations that give a growth advantage to some kind of cell. Okay. It can either be something like you turn on an oncogene, which is something that turns on the cancer part of the genome, or it turns off a tumor repressor, right? A tumor suppressor. So then if the cell wants to go become tumorous, this gene isn't being active, telling it, nah, you don't want to do that.
Not
right?
today.
Right. And then, so these are the driver mutations. Then there's passenger mutations, which are kind of like hitchhikers. They accumulate by chance. There's no growth advantage. It's kind of like just there, but it doesn't really affect the cellular machinery in the way that it like turns it on and becomes cancerous, right?
Yes.
Tumors have very few driver mutations amidst thousands of passenger mutations, okay? So there's this distribution where there's a few that are targeted for these oncogenes or these tumor suppressor genes, and then there's a bunch of noise.
Yes.
Right? And any kind of generative model like OncoGAN needs to model that discrepancy where there's a few of the stuff that matters and there's a lot of noise, right? And OncoGAN does exactly that, right? It replicates this tumor architecture by making a bunch of random passengers and not that many driver mutations, okay? And the final thing I want to touch on is these mutations have fingerprints when it comes to cancer, okay? There's characteristic patterns of mutations that give certain processes a leg up that becomes cancerous. For example, like UV light, right? UV light causes a C to T mutation. Basically, you get this dimerization where like one leg of your DNA, you know, your DNA is a twisted ladder, but one part of your ladder is going to like staple itself. Like one leg of your ladder, it's got two legs. One leg of your ladder is going to staple itself onto itself and become a dimer. And then that's going to cause melanoma, for example, right? Tobacco smoke is linked to another single base substitution that'll cause lung cancer. So OncoGAN, which is this thing that people have made, it accurately reproduces that tissue-specific signature, right? Where it's like the lung cancer is going to do this, and the skin cancer is going to do that, so on and so forth.
Yes.
It's actually learned how to do all of that stuff.
That's fascinating.
Right? And then the other thing, we're not done with all of the stuff that can cause cancer. There's also something called large-scale vandalism, right? There's copy number alterations, CNAs. This means you've taken a whole chunk of your chromosome and you've duplicated it.
Oh, okay, yeah.
Okay, so now there's a duplication or even a deletion sometimes of large chromosomal segments. So you've got large parts, like large chapters of your cookbook that are now been copied or completely deleted. You've also got structural variants where you take a big chunk of your DNA and you flip it, and now it's reversed. Now, it's just all sorts of chaos, right? Like, there's so many different things that can happen with cancer genomes, right?
That are the driver and the cause of it.
Right. And the real sort of challenge is, how do we make a single architecture, a single framework that captures all of these different myriad effects, right, into a single pipeline that then can be used to train other AI, to train other tools, right? And that's what this paper is doing. So they use something called generative AI. We've seen this a lot, right? Like a cat on a thing. This particular architecture is called a GAN. It's a generative adversarial network, okay? There's two competing neural networks. This is a very interesting way to actually train AI and to architecture it up. I think it's very cool. It's been used actually for image generation as well.
Yep.
But this time what they're doing is they're using it to generate genomic data.
It's interesting because I've been watching this space for a while, and I've seen GANs being used in the image generation context. Now mapping it to this problem set is an interesting use of the architecture of generative adversarial networks. That's interesting.
And the basic idea behind generative adversarial networks is you've got two networks, okay? You've got one that's the forger and one that's the discriminator, okay? The forger or the generator, this is the guy who's going to create forgeries from random noise and try to attempt realism. And then there's the discriminator, which is like the judge who's trying to tell whether the thing that was generated is a real thing or a fake thing. So both of these guys have the training set, which is all the stuff that is actually real. And the generator is creating fake versions of that.
Yep.
And over many, many iterations, both of these guys are going to get really good at their jobs. The generator is going to get really good at creating fake data, and the discriminator is going to get really good at telling whether it's fake or not. And it's this competing adversarial, that's where we get adversarial from, this competing effect that actually causes the generator to get really, really good at its job.
So there's a substrate of truth that these two processes have access to. One's job is to create synthetic data based on that substrate.
Yeah.
The other is to say whether you're fake or not. And because there's this sort of iterative back and forth between these two, you get to a place where, the generator has now generated something that the discriminator views as being real because it's gone through that back and forth process.
Exactly. And now it's like really good at making real looking data, right?
Which goes back to our privacy issue and some of the other things we just talked about.
Yeah. And so this cycle repeats until the generator produces stuff that's indistinguishable from the real data. And this can be used for tabular data, which is a lot of this genomic data, right? It's not like images and things like that. It's like tables of like how much of this is there, how much of this is there. OncoGAN uses something called CTab GAN+, which is just a specific architecture that's used for tabular data.
Got it.
And it handles mixed data types, imbalanced distributions. So like the distribution is not like completely uniform. You have some stuff happening all the time. Some mutations happen all the time. Other mutations are rare, so on and so forth. So this takes care of that.
It handles the complexity of this kind of data set.
Exactly. Now, the other thing that they're using is something called variational autoencoders. These are simpler than GANs. And what they do is they basically take whatever input you have, they try to squish it down into a tiny little latent space, right? And that latent space has fewer dimensions than the original data.
Yeah.
And then from that latent space, we have an decoder that tries to recreate what was originally compressed.
Yeah.
Okay?
Yeah.
So this is used a lot. This is used actually a lot in like image generation. When we have, let's say, a 256 by 256 image, that has 256 times 256 dimensions, right? Because each pixel has a value. Yes. And you can imagine if there's only 3 pixels, you can imagine putting that on an XYZ plane, right? Where every single pixel's value has to do, like the first pixel is how far it is in the X direction, the second pixel is how far it is in the Y direction, and so on and so forth. Well, now you have 256 times 256 dimensions. Every single image is highly dimensional. But if I were to take a bunch of photos of just a bunch of faces, right? The essence of the face is actually not that highly dimensional. There's always a nose in the middle. There's always a mouth. There's always eyes, right? Maybe one of the directions could be how dark is the face, right? For us, it would be like maxed out.
Very dark.
Yeah, very dark. Like there would be one dimension that would tell the variational autoencoder, this is a very dark face, right? Then there'd be one dimension that would tell it how far up in the nose is the nose and how wide is the mouth and things like that. But the fact that there is a mouth is not something that needs to be encoded in the latent space because it's always there, right?
Sense.
The stuff that's varying is the stuff that's going to be encoded in that compressed middle part, right? And then you have a decoder that takes that middle part that says, okay, how much is the how much is, where is this and where is that, and puts it into the actual image that it reconstructs. And this is something that we're seeing in MNIST. For example, the MNIST data set is a bunch of handwritten digits.
Yeah.
The key part about variational autoencoders is that it's a continuous latent space, meaning that all of my real data points are somewhere in my latent space, but I can pick any point in between and that'll result in something real. It's continuous. It's not discrete, like this and there's nothing in between, right? There is actually meaning in between. And so you can see in that latent space of the MNIST, it's going from the thing that looks like a 9, which is over here, to a 3, to a 6, to a 0, right? And it's continuously deforming. And all they're doing is reconstructing what happens if I move on that latent space, like as a walk. And I see what does the decoder reconstruct? Does that sort of make sense?
No, 100%.
It's like it's taking all of the information of the stuff that it's trained on and saying, what is the essence of the thing? I'm going to put that into a landscape that I can traverse.
You can traverse. Yeah, exactly.
Right.
You can go
and then as I move through that landscape, it's going to create meaning with my decoder.
Because there's different points on that landscape, for example, in the numbers that we find meaning in, which is like the 9, the 3, the 0. But there is this transformation,
a continuous
in between there, where you can say, oh, this is like a 9-3-ish thingy. On my way from 9 to 3.
Exactly. Exactly. So they're using both. And the key to using both is that you've got a GAN that's used for complex interdependent features like mutation counts, driver co-occurrence, that's there due to high fidelity matching. And then you have this variational autoencoder that's there for continuous variables like genomic position. The position is a continuous thing, right? But the mutation count, that's a discrete thing.
That's a discrete thing.
Right? So you're combining both into this hybrid approach to create this like realism in the data set.
That's actually really, really interesting.
They're not limiting themselves to like one type of architecture.
Right.
They're really harnessing the true power.
It's like there's this blended architecture which is using the value of both of these like modalities and taking the best of both. And sort of using them in the context that they're good at. In parallel or together.
Exactly.
That's really
exactly. Because the genome is both continuous and discrete. Right? And so now we're getting like two soldiers here that are doing the work. Right? In order to train OncoGAN, they use the training data from pan-cancer analysis of whole genomes, PCAWG. It's a data set that has 2,658 whole cancer genomes, like entire genomes. Okay? All 3 billion base pairs.
Massive.
Yeah, and this data set is treated like sensitive information because it should be, right? Because this has actual markers that can identify patients and things like that. But using that, they've now created something that will generate data that doesn't have those limitations.
They've created a derivative product from source data that is personal identifiable information that now has that degree of separation to not run afoul of the privacy.
Exactly. Exactly. And from what I counted in the paper, there's 5 GAN models and 1 TVA model. So there's 5 GAN generative adversarial network models and then 1 variational autoencoder model. All of these guys are working together to create this giant genome, right? Multiple giant genomes. And obviously the question is to ask is like, okay, how real are you making this, right? The photo that you're making, could it fool me?
This becomes with photos, it's easy because we sort of have the eye test, right?
Yes.
This is the whole uncanny valley concept, which is like, okay, I can look at something and be like, oh, the fingers aren't right.
I mean, now, dude, I'll be honest, dude, there's like videos on Instagram that I get fooled. I do a double take and I'm like, oh, this is definitely.
There's a Neil deGrasse Tyson just did a video of himself talking about how Earth is flat, and he held up an iPad to the camera. You didn't know, like the video starts, it's just Neil deGrasse Tyson talking about how the Earth is flat, And then like he just moves the iPad and he's like, that wasn't me. And it's like,
oh my God.
And it's the same, it's like him in the same space.
Oh my God.
In the same outfit, in the same voice. And it's effectively indistinguishable.
Yeah, dude, it's getting really good, right?
It's quite good.
So at least we're harnessing it for like something useful.
Something useful.
Yeah. So one of the things they looked at to see, okay, is the stuff that's being output by this neural network, is it something that can be real, right? They looked at mutational density and type. They found a high similarity between the synthetic and the real data.
Mm-hmm.
They looked at mutational signatures. They found that it's like pretty nicely correlated. The real thing that got me was the genomic distribution. So you can look at the entire genome of the human from, chromosome 1 all the way to chromosome 23 with the sex chromosomes, and you can follow where mutations are happening.
Mm-hmm.
Okay. And in cancer, mutations do not happen uniformly.
Mm-hmm.
Okay. There's going to be parts of the genome where it happens all the time. And there's parts of the genomes where there's very few mutations. For example, if you're closer to the center of the chromosome, you're not going to get that many mutations. But if you're closer to the edge, you're going to get a lot more mutations just because of the physics of like, you got a little bit more freedom towards the edge than towards the center.
Yep.
Right. And so they actually showed that mutations in their data set would follow non-uniform distribution. So on the top, they have the distribution of mutations in a real sample.
Yes.
On the bottom, you've got your generated. It looks pretty much the same.
The eye test,
The eye test, yeah, exactly. And what they've done is like the axis on the x-axis is all the genes.
Yeah.
Like all 23 chromosomes worth of genomes.
Yeah.
And they've binned it in like, I think 1 kilobase bins, and they've counted how many mutations are happening, right?
That's incredible. This is actually
it's very similar to what we would actually see.
What we've been basically able to do is now create a system that on the fly, it's not fixed.
Yeah.
It's a generative model.
Yeah.
So on the fly, any team can now take this and say, we want this kind of dynamics, and they can generate now these cancer data sets that mimic real cancer genomes to a degree of accuracy or comparable or high fidelity that is usable in practical work in this space.
Exactly. And that's that key that you just touched on, usable, right? What does it mean to be usable? Well, they actually tried to test it with something called DeepTumor. DeepTumor is another AI that's been developed to identify cancers, okay? They could fool DeepTumor really well.
Oh, wow.
But here's the key. Here's the key. DeepTumor is really bad at rare cancer subtypes. Okay? Like lymph MCLL, there's only 35 samples in the training set, okay? And if you have low mutations, you're going to struggle with like creating an AI that can identify that. Well, they substituted generated samples into the training set, and DeepTumor did better once DeepTumor trained on those. The F1 scores improved.
That's fascinating. So
right?
the synthetic data from this GAN, this OncoGAN, when fed into an existing detection model.
That's like kind of established. People use it all the time.
It's credible, all these things.
Yeah.
It has now improved its ability for these edge cases.
These like edge niche cases. Because now I can generate genomes, right, for that specific thing that's not really prevalent in a lot of the real world data sets.
Because the idea is you can take the DeepTumor and then use it on like real world patient and know that they do or do not have it.
Exactly.
And then if it comes out with the result, that is really powerful.
So it's really augmenting the data sets that we already have.
Right.
With these synthetic data sets, which, by the way, this is something that people do all the time in AI research, right? You do data augmentation, where you take whatever data you have, you like apply transforms to it. When it comes to image data, you like squish it, you'll like turn it from black and white to red, white, and blue, or vice versa. You'll try to make the model more robust to the data quality. But here, they're actually able to create new data that can target these really rare cancer subtypes and establish a new paradigm for medical AI, right? We can generate more data instead of we just need to collect more data.
Right. Which there is a bottleneck on the collecting data piece.
Exactly.
And so you can much more quickly scale if you can create usable synthetic data sets that actually map to the real world use cases in a way that is demonstrably true.
Yes.
Which is kind of the point, part of the point of this.
Yeah, exactly. And there's no one-to-one correspondence with the real patients.
Right.
You don't have to worry about HIPAA.
You solve the privacy issue while accelerating the ability to both create the synthetic data sets and then have those applied to existing tool sets or create new tool sets around all this process.
And the team already, they've got 800 synthetic genomes that are openly available. Wow. No ethics approval needed. Right. So anyone can go and try to train a model based on that. If they've got a new architecture in their mind that really is specific to genomic data, they can test it on this. It's a new gold standard for benchmarking, right? Because now when I generate some kind of data set, I have a ground truth on what type of cancer it is, what are the mutations that should be flagged, so on and so forth. So it's a catalyst for medical oncology, I think. I think it's very cool.
It's a huge new tool in the toolbox for oncology studies.
Yeah. I mean, there's still limitations, right? Like the fact that we're doing this factorization where we first create the mutations and then we have another model that goes in and distributes it across the genome. It's not fully capturing this like complex interplay between features. Like, for example, if you have a copy number alteration where you have these giant chunks of chromosome that get duplicated or deleted, that's going to influence local mutation rate. This is not something that captures that, right?
For sure.
It can't simulate complex events like chromothripsis and like tumor subclones, but it's still a huge step forward, right?
We have to. It's one step at a time.
Yes,
this has obviously been an issue that is not only affecting so many people, but it's been happening for so long. And any new step towards our ability to solve this more robustly is like hugely important.
Yeah. Because like cancer is just like, it's just such an insanely difficult problem, right? It's not a single cause,
right?
There's no single like panacea,
solution.
Yeah, it's just So any incremental, and this I think is actually a huge step because I think this opens up other people to do this kind of stuff,
100%,
to create large data sets, to then have really AI going in full-fledged,
right,
to try and help out,
right. In a way that again keeps in mind some of the aspects of data privacy that are very important when you talk about medical studies. For all the reasons we talked about at the top of the story, this is really again. We said we're gonna make sure we give Toronto,
University of Toronto. I mean, dude, their AI is
this is a big deal.
Their AI is always like on point. You know, their AI research is ridiculous.
This is a really big deal.
It's a really big deal. I mean, you guys lost the World Series,
but
we'll see you next year. Hopefully, you know that'll be great. Round 3.
Round 3. You've given us an incredible new tool in the box.
Well done on
ability to do cancer detection, and expand the amount of people that can start really working at this issue in earnest. That's our story number 1.
Yep.